So we are just a few minutes ahead on our next presentation. So that is good because we can have a kind of a relaxed transition into our next virtual presentation. And that's coming from John Brosowski from Geocom. And we also have Geocom folks in the room here as well. Excuse me. And his presentation really sort of ties back and dovetails with some information Richard Kelly was giving us yesterday with the NINA update, and this idea of these 3D spaces becoming, you know, it's out there on the horizon. It's kind of this next big thing coming along. And this idea of this vertical axis and this Z value is, I got distracted. Okay. But yeah, this idea of this Z value and Z axis and how that's going to be really, really critical out in the future. And I think we're almost there. There we go. So John, you've got the floor.
Okay, great. Can you see the full slide up on the screen right now where you are?
Yes, we can.
And my audio levels are okay?
Yes.
All right, great. I'll jump in and get started. Hi, everybody. My name is John Brosowski. I'm Vice President of Innovation at Geocom, and I'm going to talk today about a little more about this using the Z-axis to locate 911 callers. Obviously, this was touched on in the previous presentation. Maybe I'll look at it from a little bit of a different angle, including how state-level GIS programs can play a role and what else the industry might need. So I thought it would be useful to start by talking about some new developments in 911 caller positioning, or maybe a better way to put it would be to talk a little bit about the evolution of caller positioning and how at each jump in the evolution of caller positioning, each technological advancement has really resulted in increasing need for bigger and bigger GIS data sets. And if we go back many, many years, I hope you're having a good time in Milwaukee. I grew up in the area. I grew up just next door in Waukesha County. My home address where I grew up was West 214 space North 5818 Silver Meadows Drive. That's a wonderfully complex address from a geocoding and GIS perspective. Even today, it works, but it's a complicated address. Growing up as a kid near Milwaukee, and this is many, many years ago, think like late 1970s, early 1980s. In Milwaukee, one thing I remember about Milwaukee was that it had a very unique smell to it. And actually Milwaukee at the time was home to many big brewers. There was Miller, Pabst, Schlitz, and Blatz. Actually at that time, if you didn't know it, Milwaukee was the biggest beer brewing city in the world. They brewed more beer than any other city in the world. There was also the Ambrosia chocolate factory, a huge chocolate factory. And all of those smells of beer and yeast and chocolate, it just kind of combined to create a very unique smell in downtown Milwaukee. It was to the point where you could put me in a car, drive me east on 94 and blindfold me. And I could tell you when we hit the city just by the smell. So I could imagine, you know, somebody making an emergency call and saying, I smell beer and chocolate. And just based on that, maybe emergency responders could tell that the individual was calling from somewhere within the city limits of Milwaukee. Maybe you could call that an olfactory location referencing system. But let's flash forward, get a little bit more modern here. So, you know, if you go fast forward probably about 20 years or so, that's when 911 caller positioning started getting especially interesting, because that's when wireless 911 positioning was adopted. The FCC required wireless carriers to start calculating the position of mobile phones and sending that information to 911 dispatch centers. And especially at that time, that really started putting new demands on GIS that nobody had ever really envisioned or thought of. A lot of emphasis and emphasis was and investment was going on around the mobile phone positioning, and not necessarily on the GIS data that was needed in order to make mobile phone positions actionable. So at the time, and even to a certain degree today, often the first level of detail that a 911 dispatch center gets with a wireless 911 call is information about the cell tower. So the cell tower cell site that the radio signal from your mobile phone hit when you called 911. And Oftentimes the cell site information, it's the street address of the cell tower. And then sometimes it also includes some cell sector information. So if the cell site is a sectorized cell site, instead of an omnidirectional cell site, then we can also get information about which sector face of the tower your call hit. And that really created a big demand for new types of GIS data. So for the first time ever, we were creating GIS data. We were creating GIS maps of cell tower coverage areas, whether they were omnidirectional cell sites on 500-foot tall cell towers, or if they were sectorized cell sites, and we could create these sort of pie-shaped wedges or arc bands. These were all polygon geometries that we could light up on the map, and we would know that a 911 caller was located somewhere inside that that area geometry on the map. So and that put a lot of stress or a lot of demand for a new type of GIS data to be built in order to support 911 calls from cell phones when that emerged in the late 1990s and early 2000s. Of course, the next bit of the cellular wireless location was what was called phase 2 coordinate location. So in this case, wireless carriers are calculating or determining a latitude longitude coordinate for a 911 call and from a cell phone. And they're doing that using a variety of different technologies. Could be GPS in the mobile phone handset. It could be an analysis of radio signal from your mobile phone hitting 2 or more cell sites and then doing triangulation or triangulation back to get a location. Sometimes looking at the time difference of arrival of radio signal from your cell phone to multiple cell sites. And then in some cases, combining all of those different methods. But long story short, that would result in a latitude longitude coordinate. And there again, that created a huge demand for locally authoritative GIS data. If you think about it, this was kind of before Google Maps even existed. Couldn't go online and type in a coordinate yet because Google Maps wasn't there. So it created this big demand for locally authoritative GIS data sets that were capable of being interfaced to 911 systems so that you could display the location automatically of a latitude longitude coordinate. Because of course you can't read a latitude longitude coordinate to a human and have the human know where it is. There's no way to know where a latitude longitude coordinate is without plotting it on the map. So in fact, if we zoom in on this latitude longitude coordinate that we were getting, you can see that it still is not a perfectly precise pinpoint location. For example, if often we get confidence intervals that indicate how confident we are in the location that the carrier position determination equipment calculated. And for example, it could be 80 meters. So we know that maybe within a 95% confidence, 911 caller is somewhere inside that circle on the screen there with an 80-meter radius. So pretty good, way better than just a cell tower location or even a cell sector location. But as you can see, in this case, we're really not sure what side of the street the caller's on, even which street they're on. And you can kind of see the building footprints in this display as well. And we can see that, well, maybe this caller, there's possibly several different buildings that the caller could be in. So there's still cases where it's challenging to locate 911 calls in this type of a scenario. Obviously, if it's an accident outside, or there's smoke coming from a building, or there's lots of people there waving their arms as emergency responders are rolling up to the scene, then it's no problem. But tragically, there are cases every year where people call 911 from inside buildings and can't communicate where they are. And that slows emergency response. Often you have to go door to door searching. Sometimes you have to search multiple buildings, and that can lead to negative outcomes and even fatalities. So fast forward another 10 years or so, and the next big innovation hit, and that was the ability to pull device-based hybrid positioning into 911 dispatch centers. And device-based hybrid positioning is positions that are calculated by location services in your mobile phone's operating system. So on Android phones, it's Android ELS, the emergency location service that does it. And on iPhones, it's Hilo, the hybridized emergency location service from Apple. And both of those services are doing some unique things. They're calculating the location not only based on GPS in your phone, but also by looking at other information. And that other information can include things like wireless access point signal strengths that the Wi-Fi radio in your phone is detecting inside buildings. And then that can be a sort of crowdsourced or pocket sourced, if you will, back to Apple and Google, and they have information about it from 240 million mobile phones wandering around buildings in people's pockets, and that can all fit into their location computations. And what that provides is often for public buildings with good Wi-Fi infrastructure and lots of access points, and lots of people moving through buildings with mobile phones in their pockets, that can actually provide pretty accurate indoor positioning, at least horizontally. And we've had just a ton of great experience with this in real world situations where you can make go to a public building, for example, a large retail, maybe a mall environment, go into one store, make a call, go out in the corridor, make a call, go in the restroom, make a call, and then record the locations that they got at the dispatch center. And we can actually see the caller moving between these different locations. It's a level of precision that was never before possible for 911, and something that really is kind of revolutionizing 911 in some ways. Well, really what it is 911 is beginning to finally have the accuracy and the precision to truly move indoors. Of course, one of the great vendors in this space is a company called Rapid SOS. Rapid SOS is making this device-based hybrid location from mobile phones that they get from Apple and Google available to all 911 dispatch centers in the United States for no cost. And so that really reduces the barrier for this type of information. However, in some ways, having an accurate indoor position like this without an indoor map or building footprints is sort of like putting a blue dot on a blank whiteboard. It sure may be very accurate and precise, but without GIS data behind it, it doesn't necessarily give you any more actionable information than you would have had with a more coarse-grained position. So, of course, what we're finding here is that if you were to combine that position with an indoor map, now obviously you have real-world actionable information, and the folks from CRG and Datamark were just talking about this scenario, of course. So, and of course, if you begin to zoom in, you can see it's possible to pull in obviously a lot more detail about what's in the building, structure, room names, equipment, things like that, entrances, exits. But you can kind of imagine this data set is starting to get pretty big. If you think about it, there's something like 120, 130 or more million buildings in the United States. And we know that from Microsoft's building footprint database, where they extracted building footprints from aerial imagery for all of the United States and Canada, and then just counting the number of building geometries that they detected. And obviously creating this type of map for that many buildings obviously is quite challenging. Probably we don't have to map all 125 million buildings, but if we're just to map, large buildings, public buildings where if there was a major incident, it could have a large impact on human life or the community. Maybe we can get it to a smaller list, maybe 10 million buildings or something like that. But 10 million is still an awfully large number of buildings. It's a pretty big data set. And, we see the sort of the demand for, or the need for these types of indoor maps continuing to increase from the public safety perspective. As we begin to look at other new and emerging technologies, of course, IoT is a buzzword right now, but it's real. I mean, it's about tapping into sensors and alarms and things like that that are inside buildings. This screenshot here is depicting occupancy sensors that are giving counts and locations of people inside of a room. So obviously that could be very useful tactical information during an emergency response. And then if you were to combine that with outdoor and indoor positioning systems, we're beginning to see a real, of course, we're all familiar with outdoor positioning systems with GPS, but we're beginning to see lots of developments in indoor positioning systems. There's just a variety of different indoor positioning technology that's emerging, and it's getting really, really good. And if you were to combine all of this information, positions of emergency calls inside buildings with sensor information from the building itself, with indoor positioning of emergency responders and outdoor positioning of emergency responders, getting them to the scene, you begin to have this total picture that gives you an unprecedented level of really situational awareness and context as to where the emergency is happening and how to get there, and where emergency responder personnel is in relation to the incident. So that's just putting more and more demand for this fine-grained, high level of detail GIS data for public safety. Again, raising the question, where is all of this data going to come from? And then, of course, we begin to talk about the Z-axis. So 911 is definitely going indoors, without a doubt. It's also going vertical. It's going into the third dimension. So never before, when you called 911 from a mobile phone, would the dispatch center have any information about where you were located vertically. That was all up to you to communicate verbally with the call taker to tell them where you were vertically in the building. So these are some examples of some 3D maps that we built over the years. The big one here on the left, this is US Bank Stadium in the city of Minneapolis. This was used during Super Bowl 52 as the common operating picture. This is kind of like an example of a high fidelity 3D and indoor mapping system. The 3D map of the stadium was built using BIM data and CAD files from the architect and construction firm that built the stadium. And then some of the surrounding buildings that you see, these sort of gray box or shells, those were created using a combination of LiDAR as well as just multipass aerial imagery and photogrammetric methods to create three-dimensional gray box building representations. And then this whole thing was connected up to a variety of different IoT sensor feeds. There are multiple computer-aided dispatch systems, several thousand cameras that we were connected to, about 5,000 Bluetooth low-energy beacons inside the stadium that we were connected to, so that we could track emergency responders through the building in 3 dimensions, as well as via GPS outside of the venue. Access control to see status of electronic locks on doors and gates, things like that. And this was sort of, if you can think of it like almost like a study in the art of the possible. We knew that vertical location for 911 was coming, and we knew that 911 was moving indoors. We wanted to see what was possible really, if we could really make this type of 3D and indoor mapping display like people were kind of imagining in their heads. And so I think what we found was that it certainly is possible if you're willing to, spend $250,000 per stadium or per building. But obviously, with 125 million buildings in the United States, that's not scalable. Even if you just do 10 million buildings or 5 million buildings, it's not particularly scalable. So looking at some other methods are the sort of lower middle image here. This is a high school where we created a 3D map using just a hobbyist grade drone and Esri's drone to map. Just send up a drone, capture some imagery, bring it back down, run it through drone to map, and it creates a nice digital surface model and 3D map like you see here that could be useful tactically. Of course, that drone technology, kind of at the hobbyist level, that can obviously, the same technology scales across larger areas. From airborne multipass aerial imagery capture platforms, as well as space-borne remote sensing platforms as well. So we're beginning to see more and more of these types of digital surface terrains that, and models that include building information kind of become more operationally available tactically for 911 and emergency response. And then, of course, another method that we see quite a bit of is taking 2-dimensional building footprints and extruding them into 3 dimensions based on building heights. And building heights could come from a variety of sources, maybe probably the most popular being multi-return LiDAR measurements. So lots of different methods for creating these sort of 3D map displays. And once you have 3D GIS, if you have a 3-dimensional position of a 911 caller, then you can put that 3-dimensional location of the caller inside the 3D map, and you have something very tactical and useful to use. Now, however, we also have learned that 3D map displays are not necessarily easy for everybody to use. And so as we look to really scale this out nationally, we realized pretty quickly that you can communicate three-dimensional information in two-dimensional map displays via floor-aware map displays. And so, for example, here we're displaying a map of a high school and a 911 call inside the school. And then on the right side of the screen there, you see a floor selector where a call taker, dispatcher, responder that's using the application, they can sort of toggle back and forth between different floors in the map display. So in this sense, the map is two-dimensional, but yet it's floor aware. And so in that sense, it can be aware of vertical positioning and vertical location technologies. So what's really going on with this XYZ stuff? Well, the situation that we have now is that wireless carriers are beginning to send Z-axis data, and this resulted from some rules that the FCC imposed on the wireless carriers a number of years back, as well as a legal enforcement action that the FCC took against the nation's 3 major wireless carriers about mid last year, that resulted in the carriers agreeing to start sending this information nationally for all 911 calls from mobile phones when they have the information. They don't always have it, but when they do have it, they'll send it. Now, the catch here is that the information, the vertical information that they're required to send is the Z-axis information is in a measurement that's called height above ellipsoid. And the height above ellipsoid, it's sort of a common way that GPS receivers use to determine or communicate elevation information or altitude information. But however, height above ellipsoid, it's not really meant for humans to look at directly. So the ellipsoid is sort of a mathematical representation of the Earth. It's not a topographic replica of the Earth. So it's sort of this mathematical smoother surface that roughly, sort of approximates the spherical surface of the Earth. And if you think about it, that's very different from a very detailed digital elevation model that includes, accurate information about every hill, valley, nook, cranny, rock, boulder, dirt that's been pushed around by humans, buildings that have built locations higher than the ground. None of that is included in the ellipsoid. The ellipsoid is simply a mathematical model that's very easy to implement in GPS firmware and easy for GPS to calculate how far above or below this mathematical surface you are. So as a practical matter, what that means is that height above ellipsoid, not really meant for humans, can even be confusing if humans look at it. Sometimes it could even be a negative number, even if you're above ground and on the second floor of a building. So it's best not to just read that number on your 911 display and take it at face value. However, it is a good measure of altitude. And so it can be converted into a dispatchable location. And we typically think of a dispatchable location as, for example, a street address, maybe a building name, but also a street address, and then even sub-address elements like the floor in a building. So if we can convert a raw position measurement that includes a latitude, longitude, and a height above ellipsoid into a building name, street address, and floor, now we've created something that's truly dispatchable. And even at this point, we don't necessarily need an indoor map. It's obviously better if you do have an indoor map, because then you can take it further and you can get to the room level. But even just getting the street address with the floor is a breakthrough for 911, because they haven't had that in the past for 911 calls for multi-story buildings. Now, the catch is that you're probably putting this together already. This is driving even more need for bigger and bigger data sets because you really need local data in order to convert latitude, longitude, and height above ellipsoid into dispatchable locations. But yet, without this information, lives could be lost that otherwise could have been saved by utilizing this new geodetic positioning data that's available from cell phones. So we have a challenge in front of us, like where are we going to start to collect how are we going to collect all of this information? So I wanted to talk a little bit about a few different thoughts we had about this, as well as to maybe generate some ideas from you and some conversations for the remaining time this week about where this data could come from. So we think that first, starting with local government and local business enterprises, we'll get some of this data. And we're definitely seeing this today. We'll get a small number of the 125 million buildings, but it's going to be a lot of very critical buildings in a lot of jurisdictions. So it's going to be schools, K through 12 schools. Nobody ever says no to mapping a school for public safety. It's going to, hospitals, government buildings, airports, places like that, places where there's lots of people, places where if there was an emergency, it could have a big impact on human life and the community as well. So we see today, we see local government as well as some local business enterprises willing to pay for creation of this type of data. Number one, because it makes jurisdictions safer, but on the local business enterprise side, it's a sort of it promotes a life safety, it creates a life safety feature for a building enterprise and facility. You can make a building owner, operator, manager can make their building safer for their staff, guests, customers, occupants, and visitors. So still, that's not going to get 125 million buildings. It's going to get a small number of buildings, but it's going to get a critical number of buildings added into this type of a system. So where else are we going to get information? Well, even outside of indoor maps, we still need information about buildings, structures, addresses, and data, just generally data about buildings. So there's some existing data, and this is sort of the realm that one of the realms that all of you work in. As you know, there's the National Address Database, a great data store of 911 address locations. There's the 3DEP, all of the elevation program data that you're all working on. And then there's also the national map. And so the national map has a structures feature class that includes things like schools, hospitals, post offices, police stations, and so on. Interestingly, also with the crowdsourcing aspect to it, where volunteers are editing structures across the United States as part of that structures feature class. But for 911, for this new elevation challenge, where we need to convert raw geodetic measurements into dispatchable locations, we don't need just one of these data sets. We need all of them, and we need to sort of meld all of these data sets together. So these existing programs are one source of information and data that we think we need in order to solve this problem. There's, however, we still think that the problem is probably the data that we're talking about is big data. It's getting really, really big. We think it's even too big for state and federal government to take on and pay for on its own, using sort of the centralized top-down approaches. And so we think that's where geospatial data crowdsourcing can come into play. And you saw a little bit of that on the previous slide with the National Map Corps, with the crowdsourcing program for place structures. This is another example of a crowdsourcing project. This is actually a proof of concept project that we're working on in Texas. We're working with a 911 authority there, the Concho Valley Council of Governments. It's a multi-county region in Texas, as well as with the state level 911 program there, the Texas Statewide Commission on Emergency Communications. And they had this idea that they knew that they're going to need increasing amounts of locally authoritative data, including in-building data, more than they could ever afford to hire a vendor to collect and build on their own. So they had this idea, what if for some types of buildings, and they decided to start with schools, what if for schools there was a curriculum for a high school science class or technology class where students could learn GIS, they could learn what GIS was, they could learn about editing GIS data and collecting GPS points and just all of the aspects of GIS and its capabilities. And then what if one of the activities of that curriculum was to create an indoor map of the school? And so we're doing a proof of concept there today with CVCOG and also Mason High School, where there's a technology class and the kids are doing just that. They're learning how to use GIS and they're making a map of their school. They're using GPS, they're using ArcGIS Pro, they're using Web App Builder. They've got a GeoSlam scanner that they're pushing through the school. It's really awesome to see high school students just learn how to use GIS. but also produce a data product that can contribute positively to public safety of their school. So this is one example of crowdsourcing that we're studying to see if it's feasible, and if it's feasible, if it can scale across the region, and if it can scale across the region, could it scale across the state? And if it can scale across the state, can it even go further than that? So that's one example of crowdsourcing. As we think about crowdsourcing, one of the challenges is often, how do you get people to do it and to keep doing it? Because it takes people's time. And so I think, one reason that people do crowdsourcing is out of sort of what I would call an enlightened self-interest, or maybe just a positive worldview, where they want to contribute to making the world a better, safer, healthier place. That's one reason people do it. But another reason that people could do it is because it's fun. And so one way to make it fun is through a concept called gamification. And this is a technique where you take a sort of a repetitive work task performed by a human, something that's usually not fun or something that's difficult, and you make it fun. And a really great example of this that I like to look at is Malaria Spot. And so Malaria Spot is it's a game. You can go to Google or the Apple App Store right now and download it, install it on your phone. You play this game because it's fun. You get a little excitement, dopamine hit as you're doing stuff in the game and competing with other players and getting, earning in-app rewards and things like that. But it turns out this game is actually using real-world data. And what you're actually doing is detecting malaria in malaria cells and blood samples. As it turns out, there's over 200 million cases of malaria every year. A child dies every minute from this disease. It's caused by a parasite in the blood, transmitted by mosquito bites. Diagnosis time can take up to 20 minutes, and it requires a trained medical technician that has to count all of the parasites in a blood sample using a microscope. So problem is, there's not enough trained medical technicians with microscopes in the right places at the right time to keep up with 200 million cases per year. So the concept here is to take blood samples, scan them, upload them to the game, and then have thousands to millions of users playing this game to help diagnose malaria in just seconds. So that's kind of, it's one great example of gamification that, as we'll see, could be applied to big data, geospatial data collection as well. And then another technique is blockchain tokenization. And if we can combine blockchain tokenization with gamification, then we have something pretty interesting. So first of all, what is a blockchain? I know you're all aware. It's a chain of blocks. Everybody knows that. It's it's like commonly used for digital currency these days. For example, I could send you some units of a digital currency. The transaction gets recorded on a block on the blockchain. When the block is full of transactions, a new block gets added onto the blockchain. And the first piece of information that goes into the new block is a cryptographic hash of the previous block. So what that means is, if you went in and tried to edit the blockchain digital data to say that I sent you way more units of currency than I actually did, that would break the cryptographic hash, and all the other nodes in the network would realize that that version of the blockchain that you edited was invalid and would automatically be rejected. So in that sense, these sort of blockchain systems are called trustless, because you and I can do transactions with one another, but you don't have to trust that I'm honest, and I don't have to trust that you're honest, and we don't have to trust a third party like a bank. It's more or less the system just kind of runs on its own. Well, it turns out that currency is really only one type of application for the blockchain. These transactions that are in the blocks, they're just representing sort of native units. We can call them tokens being sent from one person to another person, or being burned or used for this or that. Now, you can use a token to represent anything. It could represent some unit of value that has a monetary value, like digital dollars, sure. But it can represent things that have nothing to do with currency or money. For example, a token on a blockchain could represent a unit of work. So you can probably see where this is going, where a token on a blockchain could represent, for example, a geographic data collection task. So we're beginning to see a number of geospatially oriented blockchain applications emerging. I think we're going to see some enterprise private geo blockchains emerge as well. And we're going to see just more and more of these public decentralized blockchains emerging, and then some kind of hybrids of the two. But what's really interesting is when you start to combine blockchain tokenization with gamification for geospatial data crowdsourcing. And so there's just a couple of examples on the screen here. This first one is called, this app here is called Coin. And the app was created by a company called XY Labs. And basically what this app is doing, it's a little app you can put on your phone, and you move around with your phone, and you hit the button, and you're collecting some geospatial data about the location that you're at. You're basically GPSing it. Then there's some options to do verification of place names, business names, things like that. And every time you do that, you get rewarded with points. You get this little dopamine hit because these points are flying around the screen. It's fun. You're competing with other players as well. But then because these in-app reward points, they also correspond to tokens on the XY network blockchain. So you can actually extract or convert your in-app rewards to tokens on the blockchain. And then you can go to just any cryptocurrency exchange and exchange those for other cryptocurrencies, Bitcoin or US dollars or whatever you want to do. Now, it's just really interesting because when the XY Labs created this, they created these tokens out of thin air. They had no value, but then they created an application that had utility. And over time, those tokens came to have some value. But what that has created is a system of incentivization. So one other thing that can drive crowdsourcing beyond just you do it because it's the right thing to do, or because it's fun, because you like it, you want to make the world a better place, or because you're playing a game and the game is fun. Another way to really drive and grow crowdsourcing is via incentivization. And blockchain tokenization creates a mechanism for incentivization that's pretty interesting. Now, another example here is maybe a little more cartographically oriented, or something geographers would recognize, is another app called Foam. Check it out. On Foam, you can curate consensus-driven map. And again, as you're contributing, you're earning some rewards on the blockchain as well that you can decide what you want to do with. These are just a couple of examples. We do think that this blockchain technology is about to hit GIS probably in a big way. We haven't heard probably a lot about it yet, but if you think about it historically, within the last decade, we've been seeing other technologies sort of collide and become integral with GIS. So, for example, 3D GIS. Well, 3D was always a thing, but it was so commonly somewhat difficult to do 3D GIS, three-dimensional GIS. But really, within the last several years, it's gotten a lot easier. Certainly, compute processor power has increased significantly, and with the emergence of GPUs, or graphics processing units, commodity-grade GPUs. The ability to do three-dimensional visualization really became possible to do on commodity gear. You didn't need $20,000 computers. You could do it with a normal PC, a laptop, or even a mobile phone. So we began to see 3D collide with GIS, and then along with that, we began to see BIM sort of collide with GIS as well. So GIS is often used as a system of record. BIM is also used as a system of record for buildings. GIS is spatial, BIM is spatial. We began to see the two kind of collide, and GeoBIM sort of emerge, and now BIM is just a kind of a standard integration or use for GIS and facilities management and other types of building management systems. And maybe another example would be what we see going on with IoT sensor feeds. So there again, IoT on sort of the real-time side of the fence, where in the past, it was maybe difficult to get real-time data into GIS, but now it's becoming more and more common and more standardized as IoT gateways are emerging, and products for bringing real-time dynamically moving spatial data into maps is just becoming sort of commoditized, if you will. There's probably other examples as well, maybe not as far along yet, but I think one of the other technologies that's going to collide with GIS is camera technology. We certainly for years, We've all had the ability to click on a dot on the map that's attributed with a hyperlink to a network camera URL to pop open a camera feed in another window. That's not what we're talking about here. What we're talking about here is actually geographically, spatially referenced video frames and objects inside video frames, so that identifying a location on the map can queue up the right frame, and identifying an object in the video can identify the feature on the map. We think that that's about to sort of collide with GIS as well and permeate its way across desktop, web, mobile, and embedded mapping applications as well. So just like those other technologies are colliding with GIS and creating a lot of change, we think that blockchain is about to collide with GIS as well. And blockchain tokenization and gamification that provides a system of incentivization. Again, think of it like this. So this XY app, this coin app, now has 4 million users. 4 million people are playing this on a daily basis. I think about our company Geocom and like what we did at US Bank Stadium. Sure, we could go out to US Bank Stadium and map the heck out of the stadium, and I could take the same 10 people and go somewhere else tomorrow. But I don't have 4 million people that I can send out to collect data. None of us do. So this is sort of think of like the sharing economy, the Uber, the democratization or decentralization, if you will, of crowdsourcing through blockchain tokenization and incentivization combined with gamification. So that's basically what we wanted to talk about today. So, when we think about what's going on with these new, very raw position measurements that we're getting from wireless carriers, we need data in order to convert those raw position measurements, raw numerical position measurements, into something that's actionable. It doesn't always have to be an indoor map. Indoor maps are great. But even if it's just a building footprint that's attributed with building name and address and some information about the buildings, and if we can get surveyed information about a building, like elevations of floors, that's even better, and or building heights, things like that, number of floors per building. Those are the types of big data sets that 911 now needs, because we're getting these new raw position measurements that otherwise are like meaningless for humans unless they're converted into dispatchable locations by using local data. So I guess our ask would be, if any of the topics that we talked about here today resonated with you, if you're interested to talk about any of these for partnerships in your state, collaboration, proofs of concept, anything like that, please let us know. Ty and Greg and Patrick are there. Track them down, send me an email. Also, if you have any feedback about any of what we presented today, both the good, the bad, and the ugly, let us know, including if you think we got something wrong or missed something important. Please let us know. We know that we don't know everything. We don't know what we don't know in some cases, and we think we love to learn from folks such as yourself that have been there and done that. So that's our appeal with this presentation, and that's all I had.
Thank you, John. And we have about I think about 9 minutes maybe for a few questions. Jamie, I'm going to throw you a little bit of a curveball, because I noticed there was a few questions and comments that had sort of stacked up in the chat. So let's go straight to those, and then we'll come back to anybody in the room.
Sure thing, Jonathan. And Matt Zmalzek from the U.S. Census had a question. So Matt, I invite you to come off mute.
Thanks, Jamie. Can you hear me?
Oh, you're breaking up a little bit. Are you having internet issues right now?
Yeah, maybe a little bit. Let me try that.
That was a little better. Why don't you give it a shot? Maybe not. I'm happy to read his question, everyone. How do you know if the gamer, and this goes back to the portion where you talked about gaming, is providing accurate information when earning the token? Do you have any information on that?
Yeah, it's a good question. You don't. Well, some of the applications that I showed, like ones that use GPS, would be pretty difficult to spoof GPS. Typically using algorithmic approaches, AI and machine learning, it's possible to implement monitoring algorithms that can detect sort of anomalous activity if we think somebody's trying to game GPS or not. Again, Geocom's not a provider of those applications, so that's just kind of speculation on my part. Another way to do it is by sort of averaging and consensus. So rather than just taking one data point from one user, you take lots of data points from lots of users, and then sort of eliminate the outliers, and then can kind of get some agreement on what information ought to look like. Certainly, you know, think of like OSM and how OpenStreetMap does it, sort of a consensus-based type of approach. Those are other approaches as well. It's a good question.
And John, do you see Matt's follow-up question there in the chat? He said it's hard to fake the location info, but what about the attribute information?
Yeah, I can't, I'm just sharing my screen right now, so I don't see the chat on here. Maybe if I just click the chat button. Yeah, there again, yeah, it's about, you know, there's different methods for that, but, you know, there again, often has to do with looking at responses from lots of different people, data from lots of different people collected for the same location, as well as like scoring and ranking of game players themselves. So trust level of players in games can increase or decrease based on their level of congruence with other players that have provided information, as well as how much information they provided over time. But definitely, it's good questions.
And Jamie, if I recall correctly, I think Joanne from Washington had a question about privacy.
You're right. Thank you, Jonathan.
Hey there. I did have a question about privacy. This was a little bit more back onto the first part of your presentation with some of the information from cell phones coming in, et cetera. And all I would say is that in Washington anyway, it seems like every legislative session, we have more and more legislation about privacy and more questions coming up about privacy. And actually, geography is starting to get into the mix, even in terms of aerial imagery. And I was just wondering how you handle that and any experiences you might have about various privacy laws that are popping up.
Yeah, you should definitely check on legislation around location privacy for when you call 911 from a phone. Typically, when you call 911 from a phone, you're giving up right to your location privacy, only for your location to be used by the 911 dispatch center. So it's not like using your location for mobile advertising or something like that. So yeah, it's definitely a big issue who can see your location, and 911 is very aware of that, as it has been really for the last 20 years. Because when you call 911, your location is made available to 911 dispatch center. Even if you're calling from a landline telephone and you have an unlisted telephone number, your address location is going to be shared with the 911 dispatch center via the enhanced 911 network when you make the call. So making a 911 call is kind of like implicitly giving permission to the 911 dispatch center to use your location. But it is a good point. You know, especially as we look at like indoor location tracking systems. So there are indoor location tracking systems, including Wi-Fi systems that can do indoor positioning based on analysis of Wi-Fi signals from your device. They can even do anonymous tracking. And some people have been using those to, for example, do business analytics or facilities analysis to identify how many people are traveling through a room or visiting particular spots in a building. And they are definitely running into very thorny location privacy issues for those types of applications, even when the location tracking is aggregated and anonymous. So those are really good questions. But definitely check legislation for location privacy with respect to 911, which might be a little bit different for that use case.
Hi, John. This is Dan Ross with NewsCheck. As you were talking about crowdsourced data, we in government have tended to shy a bit away from crowdsourced data because we've been coached to understand the lineage of the data, and it would have to be something, and the validation of the data, and it would have to be something that could stand up in court. That's one of those things that government always worries about. Any thoughts on that as crowdsourcing becomes more of a popular approach to gather important data?
Yeah, I think it's a good point, Dan. And even certainly in the 911 scenario, we could even envision like an indicator of where location, where data originated from. So if it was locally authoritative and it came from local government that went out and surveyed it, that's one thing. But if it was one of these crowdsourced data entities, perhaps it could be attributed differently and it could display differently on the screen or with a disclaimer or something like that. Time and time again, when we talk to emergency responders, they prefer some data over no data. And if they have something to work with, they're used to going out in the field and figuring it out. But a lot of folks we talk to just are really hungry for this type of data. But yeah, it's a good point. Maybe like a data scoring or data grade or data source attribute would help a little bit.
I thank you, John.